Hi everyone, my name is Zeyang and I'm a fourth year chemistry major student in UCI. Glad to see you all and thank you for listening to our presentation.
Hi, I'm Ethan Herisse. Our presentation is on Mirena or Levonorgestrel synthesis. In this presentation, we will be discussing the general reaction for the synthesis of levonorgestrel and highlight some suggestive mechanisms that take place in the synthesis. We will then discuss some applications and limitations. So, what is levonorgestrel? Levonorgestrel is a synthetic progestin, which is a type of female sex hormone that is often used in hormonal contraceptives. The contraceptives that it is commonly used in are emergency contraception pills and IUDs. Levonorgestrel works by inhibiting the release of an egg from the ovary and reducing the likelihood of fertilization. It also changes the cervical mucus to make it more difficult for the sperm to reach the egg.
This is the overview of the full suggested reaction. And on the right side, there are the references for each step. For the first step, it is a Grignard reaction. The Grignard reagent here is the bromomagnesium binding with the ethylene group. The carbonyl turned out to be the alcohol, and the ethylene group was attached to the tertiary carbon. The yield was 92%. In the second step, the 5-member ring was attached, and the yield was 45%. In the third step, it is an intramolecular reaction, and DSI was used to help forming the 6-member ring in the middle. The yield was 95%, but it took 4 days to process this reaction. In the fourth step, lithium aluminum tetrahydride in diethyl ether was used to reduce the carbonyl group into alcohol group, and the alcohol group is cis with the ethyl group. In the fifth step, sodium boron tetrahydride in methanol group was used to reduce the double bond in the 5-member ring. In the sixth step, the lithium and liquid ammonium was used to reduce the benzene ring into 1,4-hexadiene, and the double bond in the middle was also reduced.
In step 7 of the reaction, we begin to focus on smaller pieces of the molecule to eventually reach levonorgestrel. Here, the OH group gets changed into a ketone after being reacted with sulfur trioxide complex in dimethyl sulfoxide, followed by triethylamine. The yield for this reaction is documented to be 85%. Step 8 of the reaction is an alkylation carried out with acetylene and potassium tert-butoxide in THF. The mechanism of this step will be highlighted later, and the yield for this reaction is documented to be at 75%. In the final step of the reaction, sulfuric acid is used to create the ketone present in levonorgestrel with a yield of 84.6%.
The mechanism that I would like to go over is the Grignard reaction, which is at the very beginning part. So the Grignard reagent we use this time is the MGBr binding with the ethylene group. So the electron from the Grignard reagent attack the carbonyl carbon on the 6-member ring and push the electron onto the oxygen to form a negative charge on the oxygen. And then the oxygen grab the proton from the solvent system and form the tertiary alcohol. Also, our wanted ethylene group was also attached to this carbon.
For the suggested mechanism in the alkylation step of the reaction, we first need to deprotonate the alkyne with potassium tert-butoxide, as shown here. The resulting acetylene ion attacks this carbon on the ketone and the electrons are pushed up to the oxygen. In the next step, the oxygen gets protonated, bringing us one step closer to synthesizing levonorgestrel. The main purpose of levonorgestrel is to prevent pregnancy, and there are two commonly used contraceptives that employ levonorgestrel to achieve this. The first is Plan B, or the morning after pill. In this form, levonorgestrel stops ovulation by binding to progesterone and androgen receptors. It also prevents fertilization by inhibiting follicular rupture and the release of a viable egg from the ovaries. Plan B is advised to be taken within 72 hours after unprotected sex, or after a contraceptive failure such as a broken condom has occurred. When taken correctly, Plan B can be up to 87% effective in preventing pregnancy. The second form is a hormonal intrauterine device, commonly known as an IUD. Mirena is a brand of IUD that releases levonorgestrel once inserted into the uterus. The way levonorgestrel works in an IUD is by increasing the thickness of the cervical mucus, slowing the movement and impeding the survival of sperm, and acting as an effective barrier from fertilization. Levonorgestrel is the active ingredient in many different brands of IUDs, such as Skyla, Kylena, Loletta, etc. One of the most effective forms of contraceptives, IUDs, and Mirena specifically, are incredibly effective at preventing pregnancy at up to 99% for up to 8 years.
However, there are some limitations of levonorgestrel. The first thing is the lengthy synthesis process. Once again, levonorgestrel is a synthetic progestin, so there are many different ways to synthesize it. The suggested reaction in this presentation is only one possible way to synthesize levonorgestrel. Due to this, there is no one known mechanism for levonorgestrel. The processes researched to synthesize levonorgestrel have multiple steps, most of which with long reaction time. For example, we presented 9 steps, and one of the steps take 4 days to process it. The morning after pills have side effects, more commonly like irregular periods or mild bloating or blurred vision, and less commonly there are dizziness, headache, or heavy bleeding, and something like that. For Mirena side effects, the first thing is it must be inserted by a healthcare professional, and pain, bleeding, or dizziness may occur after insertion. Abnormal pain or bleeding may also occur, and the perforation is very serious since no longer prevents pregnancy and can potentially cause internal scarring or bleeding. And Mirena would be need to removed if this were to occur. And expulsion of Mirena may also occur. That will be all of our presentation. Thank you for listening.